brazing last time, and I went through some of the advantages and disadvantages. We also had talked once before about the fact that thinner joints are stronger. I think we talked about that. It turns out, if you want to do an analysis, and this applies to solder joints or adhesive bonds, well, we certainly talked about adhesive bonds, and the thinner they are, the better they are in terms of strength. But it applies to solder joints and braze joints as well. And the way to do this is, and I decided I'm not really going to solve the whole differential equation, but you can write a differential equation down from this. Remember the first day I solved one differential equation just to prove I'm a faculty member. I decided I don't have to prove I'm a faculty member anymore. But it's something called contact strengthening in the braze alloy literature. And basically, if I have a strong material on either side and a softer material in between, and typically the braze alloy will be a little bit lower strength than the material that you're brazing to. And you take out a little volume element of that braze and you put the whole thing in tension, so you're pulling with sigma YY. There should be a sigma YY down here. It turns out that as you pull this, the stuff wants to pull in, and that because of that, there's a what do you call it? There's Poisson's ratio that basically says if I'm pulling sigma YY, there's going to be sigma XX, compressive kind of pulling in, a stress trying to pull it in due to Poisson's ratio. And if the height of my braze alloy is H, I will have a differential stress as I move across here, sigma XX times H here, and sigma XX plus d sigma XX times H here. There is the volume element right here on the edge. There's sigma XX is 0, but the material here will be constrained by the material over the material to the right of this will be constrained by the material to the left of it, and the material over here will be constrained by all this material to the left of it, in terms of it has to drag that other material along in order for this joint gap to open up. It turns out if you resolve the forces in the x direction, and there's these other forces, there's a friction coefficient, if you will, times sigma YY dx, which is this little arrow here. So you've got this arrow going this way and this arrow going that way, and the difference between these two is just d sigma XX times h, and that's going to be balanced by these arrows, which is eta sigma YY dx. And if you say that these are principal stresses, which approximately they are, you can say sigma YY and sigma XX, the differential of both of those are equal. They don't have to be equal, but the differential is equal. And you end up solving that differential equation and you get this. Okay? Well, what's that look like in practice? In practice, it looks like this. Basically, you have some yield strength to your braze alloy, and if you take different volume elements here, you'll find that there is a, if you want to think of it, a constraint term that increases as you go across here, and it increases as the exponential. Okay, sigma YY over 2 tau Y. 2 tau Y is the yield strength of the material, and it increases exponentially from either side, and it gives you this thing right in here. In deformation processing, when you're rolling sheet metal, this is called the friction hill. This is not deformation processing, but the differential that we solved is exactly the same. If you know Moore's circles, and you guys ought to know Moore's circles, right? Do you know Moore's circle? And you know Moore's circle? Okay, everybody knows Moore's circle? Okay, so the Moore's circle here, we basically have the neutral point here. We have sigma YY, sigma XX, which is slightly compressive because of Poisson's ratio. So this is just new sigma YY, if you will, right here. Right here on the edge, it looks like this. But over here, this whole thing has moved over. Tau Y is still the same. Circle doesn't get any larger. We get to the very center, and it's moved all the way over here. Tau Y is still supposed to be the same. But the whole thing is moved over. I have a state of triaxiality of that amount in the center. And so by pulling on this thing, But the fact that it's bonded, the brazed alloy is bonded to these other two materials, I create a state of triaxial tension in the center. And the material doesn't want to yield because of the triaxial tension state. The stuff yields by shearing, not by triaxiality. So it turns out from that you can conclude that you actually, and people have done tests, I'll show you the test just here in a second, and show that you actually can get a stronger joint if it's a thinner joint. A little bit too far. And this is in one of your handouts. But basically, this is the joint thickness versus the tensile strength, and this was essentially, let's see, I don't know if it says steel. It's silver, yeah, 4340 steel. Silver brazed joints in 4330 steel, and the tensile strength of the pure cast silver is only 15 KSI, but in fact, when they pulled these things in tension, they got, in some cases, if they had just the right joint thickness, they got 110 KSI. Now, there's a lot of scatter here. In some cases, you don't get any more strength from the brazed alloy, but the maximum tends to follow something like this. When I get down here to less than 10 to the minus 5 thousandths of an inch, now we're talking about, that's 10 millionths of an inch, okay? That's a very, very thin brazed joint. And in fact, the material doesn't flow very well. You've got lots of voids down in here. But if you can get a void-free joint without any defects in it, you can get extremely high strengths somewhere down around when you're at something on the order of, let's say, well, in this case, less than 100 microinches thick, which is actually pretty thin. But in fact, you do get a stronger joint, not in all cases. There's lots of scatter down in here. Here's another plot. These both come out of the brazing handbook, by the way. So it was the brazed guys who figured this out. Shear strength to brazed joint thickness. This is not on a log scale on the bottom. This is a linear scale. Once you get below 1,000ths of an inch in diameter, you start getting a significant increase in strength. So it's a similar type of plot. So most of our brazed joints are in fact 2 or 3 thousandths of an inch thick, and we don't see that. But in fact, if we did something to try to get thinner brazed joints, we would see some significant contact strengthening. And it has been used from time to time in various things. Now the problem with contact strengthening, it only works in tension. It doesn't work in shear, because if you're shearing that joint, who cares about hydrostatic triaxiality, tension, hydrostatic tension, triaxiality. It really doesn't make any difference. So, but you should be aware that contact strengthening exists, and thinner joints are stronger. Just to tell a story, I alluded to this once before. These are pieces from the first version of the internal cooled Recuperator. You guys are surface guys. What's the ICR? You know what it is? Yep. And I guess they've got it on some ships now, but this was probably 8 years ago or so. The Navy had a big program to basically use the exhaust gas heat to preheat the air coming in to the turbine on the ships. Okay, and it turns out that when you're, is that, no, it's different. Okay. When you're operating at full power, which is a very, very small percentage of the time, it doesn't really make a whole lot of difference. But when you're at low power, which is most of the time, and below, 30% power is something like 90% of the time that you're operating, because you're just out there cruising around, on this nice cruise on the ocean, right? As you're scraping rust, as you're scraping rust off the rest of the vessel. But in any case, the problem nowadays is, if you're in a carrier battle group, the carrier is the oiler as well, I guess, right? Carries the oil, okay? And so the destroyers, who can't carry that much oil with them, have to come in to the carrier or to the oiler, wherever it is. But nowadays, well, in the old days, I don't know if this is true nowadays, but in the old days, people were worried about a someone setting off a high altitude nuclear attack, and you needed to have the carrier group spread out by 30 or 50 miles or 100 miles or something. Anyway, it could be 30 miles for the destroyer to come back to get refueled on the ocean. And it turns out their time just going back and forth to get fueled turned out to be a significant fraction of their time, you know, their took away from their time on station, or whatever you call it. Is that the right verbiage here? Okay. So you're sitting there going back to get fuel all the time. And so if they could improve the efficiency, one way to improve the efficiency is if you use the exhaust gas when you're not running at full power to preheat the incoming air, and you could increase and get a fuel efficiency increase of like a factor of 2 or 3 for these low power operations. Okay, it's pretty dramatic, and all of a sudden the time on station just went up dramatically, or the time while not on station, while going back for fuel, went down dramatically. Maybe the time on station didn't go up as dramatically, but the wasted time off station went was significant. So it was, I think it's owned by Northrop now, but at the time it was owned by, or maybe it was owned by Grumman then. Anyway, originally this was a facility in Sunnyvale, California, that used to be owned by Westinghouse when I visited it the first time. But that was 25 years ago, and then it got sold. And I don't know if it's General Dynamics or Northrop Grumman or whoever right now. But anyway, this is where they built the or outfitted a lot of the stuff for the Polaris and Poseidon missiles, and they make some of the biggest gear hobbing machines in the world. In fact, it's an interesting story about this plant. They started there in Sunnyvale. Why would anyone put a heavy manufacturing plant in Sunnyvale, California? Well, they put it there after the San Francisco earthquake. They had the plant in San Francisco, and during the earthquake, what was 1906, it just leveled the plant. So they went down to Sunnyvale, which at that time was just a bunch of grape fields, grapevines and stuff, and so they put the plant here. Well, since then, in the last 100 years, Sunnyvale has kind of grown up around it, so you're in the middle of this very, very high-priced neighborhood, and they got this huge plant surrounded by neighbors who don't particularly appreciate them anymore. In any case, these guys had the contract to develop this, and so they were going to basically need a heat exchanger about the size of this room, okay? And so these are parts of the heat exchanger, which are all brazed together. They built the whole heat exchanger and put it in a furnace about larger than this room, and it's nothing more than stainless steel in waffle shapes. There's big ones and little ones because you got to have cross flow, right? One's the incoming air and one's the outgoing exhaust. Well, the bigger ones are the outgoing exhaust, and the incoming air, which hasn't been heated up to high temperature to balance your mass flows and stuff, is the smaller stuff. So this is one part of it, and this is another part elsewhere. Pass those around. All brazed together. It's a pretty neat brazing job that these guys did. And it turns out they had built these recuperators for land-based turbines. A lot of the utilities, Pennsylvania Electric, Philadelphia Electric, and others would use these things to improve the efficiency of their overall operation. The problem was that the Navy, let me back up, the public utilities, when they shut down and start back up, well, first of all, they're running continuous for long periods of time. And their startup, they can start up the system slow and take 30 minutes to start letting everything rise up in temperature fairly quickly. The Navy had a requirement that you had to go from dead stop to full power in 2 minutes. And this is the early 90s. Peace had broken out, and budgets were low, and they decided that they could save some money by not doing a big full 3D heat flow analysis on this recuperator. So they just did a 2-dimensional analysis. And the problem was when they actually built this whole thing, they took it to England because Rolls-Royce was the partner that had the turbine. And they ran it. This thing was supposed to have a 100,000 hour life. 100,000 hours, about 12 years, continuous. And they ran it and found that it had, so far as I could tell, it had a life of less than 1 minute, maybe 2 minutes, before it tore itself apart. The problem was no one told the gas that it was supposed to go through there symmetrically in 2 dimensions, okay? Well, the model had shown it in 2 dimensions. Of course, there was symmetry in the 3rd dimension, right? And the gas didn't know that it had to go through this recuperator symmetrically. And think of it, something the size of this room, and had a door on the front, which was kind of the size of a garage door, but still spread out, and the thing didn't heat up uniformly, and it just, think of the thermal mass of the thickness of that stuff, and it turns out to only be a couple of minutes, okay, if you're talking locally, right? And the thing just twisted itself in two, and they had posts holding this whole thing together that were like 4 or 5 inch diameter, solid steel, hardened steel, and they just twisted. Okay, pretty amazing what thermal stresses will do. So it didn't last quite as long as it started leaking, and it was a $300 million program. And I've been told by students in the class since then that they actually did fix the problem. I was on what they called a blue ribbon panel to try to figure out why it occurred. It wasn't too hard to figure out why it occurred. Okay, the thermal stresses just tore the thing apart, because they had this 2-minute heat up requirement. Okay, if you had taken 30 minutes and kind of throttled the stuff through and let it kind of warm up slowly, everything would have been fine. So anyway, types of mistakes that come when you're rushing things, and they were only rushing things because they were trying to reduce costs. And the big thing back then was that right after the first Gulf War, and the big thing then was rapid prototyping. Everyone had to prove that they could put things out very, very quickly. And in fact, we haven't talked in here about the X-33 space program, but the X-33 was the space plane that was supposed to replace the space shuttle, because NASA knew they had lost the Challenger, and in the mid-90s they let out a contract to build an X-33 space plane, and I didn't bring it with me. I passed it around before. This is this honeycomb composite and stuff. And it was a structure to hold liquid hydrogen. It was twice the size of this room, maybe 3 times the size of this room. And it was a $1.3 billion project, and NASA had the goal that they were going to go from issuance of the contract to first flight of the vehicle within 33 months. Okay, and that's this is the prototype that's supposed to replace the space shuttle, which is pretty complex. But that was the big deal back in the early 90s, is time to market. It costs you a lot of money when you're building something expensive to have it sitting there being manufactured. So you could reduce your costs by squeezing the development time. It's just the managers who kind of came up with this wonderful news that you can save money by doing things quicker, didn't realize there's a few engineering details that have to be worked out along the way. And if you cut the time down shorter than those engineering details work, then you got a big problem. Anyway, so they've kind of backed off